All right, so I made this presentation about math and spirituality, and I am just going to make a little recording of it going through the presentation because I am pretty proud of it. Hopefully, you will enjoy it as well. It might get broken up into a couple videos. We'll see. Wonder if I'll be able to clip this out, but who knows? All right, so mathematics, and spirituality, or if you prefer, you can call it math and philosophy. These are two of my favorite things. I got my master's degree in mathematics, an undergraduate degree in mathematics, but I also got an undergraduate degree in English and have been getting much more into spirituality. And historically, would have not thought the two things overlap at all. And the more you get into some of the deeper mathematical topics, the more I realize that they actually have a lot in common. There's a lot of overlap that we just kind of gloss over in most of our math classes. I want to start with just kind of what is mathematics that most people just think, oh, it's formulas, it's equations, it's solving. And all those things are true. But on a really simple level, I think that math is the abstract science, like I say, trying to make sense of the world. We're trying to make these observations, measurements, um, translate things into this conceptual context where you can solve equations and then reinterpret them back in context of the real world. Like, for example, the number two doesn't exist unless it has some sort of a context. I can talk about having two fingers up, but if I just say two without any sort of context, doesn't really mean anything. Right? So math is this sort of language that we've created, this way of discovering the world and trying to make sense of it in a way that we can now decipher and play around with it. So some of the ideas that people often think of math are these familiar topics, and then I wanted to compare those to some more interesting ideas that most people, depending on your math background, probably never will get to experience because we require you make it through these familiar topics before you get to the more kind of complicated ideas. So Euclidean geometry is doing geometry on a flat surface, triangles, squares, area. That's what most of us are used to. There's also non-Euclidean geometry, which is now doing geometry but on different surfaces. Instead of a flat plane, what if you do it on a sphere? What if you do it on some sort of a hyperbolic plane, like this saddle point here? And the rules of geometry actually change. If you're on a sphere, you can have two lines that are parallel at one point that will intersect when they reach like a pole, for example. If you think of, I think latitude or longitude, the ones that go north south, at the equator, those lines are parallel, but they will intersect when they reach the poles at the top. So algebra, so this is what most of us are familiar with when we think of algebra, solving basic equations, solve for x, square root, squares, etc. Abstract algebra is now applying the same sort of rules of algebra, but to completely different systems. An example that some people are more familiar with is linear algebra, where instead of just solving for individual numbers, you're using an entire matrix, which could represent a whole bunch of different values at the same time. And you can still um, create an entire system of mathematics or algebra and algebra to apply to these different structures, in this case, matrices. Trigonometry, most of us are familiar with, sines, cosines, angles, one of the most applicable fields of mathematics. Probability theory. Some of us have been introduced to probability theory. It's a very relatively new in the grand scheme of things. The Greeks were doing trigonometry and geometry thousands of years ago. But probability theory didn't really rear its head until like the 1300s, 1400s, because most explorations into things like gambling or quote casting lots was shunned by religious figures. They thought it was the will of God, and so there's no reason for the average person to get into it. But of course, people are greedy and eventually wanted to start gambling. So any sort of study into these games where you could have an advantage on your side was motivation for probability theory, which became developed and is now very, very rich. I mean, all of statistics is essentially based off of it's an applied, it's an application of probability theory. Calculus, this is where many people kind of tap out on their mathematical knowledge. Some people will also do linear algebra. And then combinatorics, this is uh, my area of subject. I was very interested in discrete mathematics when I was doing my master's. So I figured I had to at least give it a shout out. If you've ever seen the movie Good Will Hunting, what they're doing is discrete mathematics, which is mathematics using integers. What we're looking at here are graphs, specifically graph theory, and it is a bunch of sets of dots and lines. And these are complete graphs, meaning every single dot is connected to every single other dot. So kind of a very basic introduction to combinatorics or graph theory. So what is spirituality? Spirituality is, again, sort of an exploration. This idea that we are not limited to just this human body. We are not just limited to our ego or thoughts, but there's something more happening and trying to investigate that to the best that we can, right? How do we make sense of the world? Many people turn to religion, but religion is just kind of one area within spirituality. Again, I think that it's just another exploration of the unknown. We're trying to figure out more about the universe. Maybe it's not the physical universe so much as the sensing, the feeling universe, but it's still an attempt to go beyond ourselves to gain a better understanding of the universe. So, some of the ideas in spirituality, religions are sort of dogmatic, specific paths that you can take. Here are the rules, here are the practices, here is an icon, all of which we're specifically aiming towards. There are many different practices, meditation, yoga, getting into nature, prayer is a big one in a lot of religions. And often some themes that we're investigating in spirituality are death, love, compassion, mortality, the limit of the self, the interconnectedness of everything. Um, Something that's going to be very relevant in this talk is the infinity of everything. So, these are just some of the ideas that were covered by spirituality. So, and it's very, very broad. I'm going to talk about where I think mathematics and spirituality overlap specifically. But before we do that, and I promise this is relevant, we're going to go back, do a quick little history lesson on number systems. So most of the math that we do is credited to the Greeks. They are just the ones who sort of formalized the math that we use today. And their civilization um, was very, established, and so lots of people had time to devote specifically towards education, and they formalized mathematics in a way that no other civilization had done quite as well, or at least this is the one that has continued to stick around. But there's many other civilizations that contributed very substantially to mathematics. So some examples, Sumer and Babylon, so Sumeria, discovered the number zero, which we all totally take for granted. But at a certain point, I mean, if you're just counting things, um, you would usually start with one, some sort of a system going up. But representing nothing was actually a major deal in the terms of number. China discovered negative numbers, another huge advancement because you can't tangibly see negative numbers, and yet their role in our world is pretty undeniable. Right? But it's pretty conceptual. Right? You can't really visualize negative of something. Egypt was one of the first civilizations to solve quadratic equations. Quadratic equations being things with x squared. So Pythagoras, who is 6th century BCE, is a Greek who is credited for sort of quote discovering the rational number system, which is denoted with this Q. Uh, we're going to now kind of talk more about this system Q, um, and and Pythagoras a little bit, right? So we're going back to the Greeks, but I wanted to give a shout out to some of these other cultures. So what is a number system? We actually are all very familiar with them. If you've ever been in a math class, if you've ever counted, you are using some sort of a number system. So it's something that we don't really talk about very much, or if we do, we gloss over it pretty quickly. Um, Most basic foundational number system are the natural numbers. So 1, 2, 3, 4. I tend to add zero. That's up for debate. Some people say you can't include zero in the natural numbers. I Googled Wikipedia to double check, and I've seen it both ways. So I like to include zero because to me it still seems like a natural number. But if you want to say it's not, that's fine. So the natural number systems is 1, 2, 3, 4. So the integers, but the positive integers. It is countably infinite, meaning it goes on forever, but we could theoretically count every single number in this system. So lots of ancient civilizations had some version of this. We use a base 10 system, so we go up to 9 digits, and then we add an extra um, digit place, right? So 1, 0 for 10. Other cultures had like a base 11 or base 40. I don't know what they are, but instead of having 10 symbols and then starting an extra count, they would have like 40 and then they would start an extra. So even this is like the number system that we use is um, is one specific number system we could have used. So the integers is an expansion of the natural numbers. Again, if you remember, we said that China discovered the negative numbers. It was credited with discovering the negative numbers, which is huge. You're now essentially doubling the size of the natural number system because now we have all of these negative numbers, which again, very kind of crazy thing to add conceptually to counting. It is now going all the way to negative infinity to positive infinity, but only the integers themselves, right? So -1, 1 to -2, 2, these whole sorts of numbers. However, the integers is also countably infinite. And I have a little demonstration right here. One goes, the first number is 0, second number is 1, third number -1, fourth number 2, fifth number -2. But in that way, we can create this one-to-one correspondence so that I could theoretically align every single number in the integers and count all of them. So again, we consider this to be a countably infinite set or a number system. So the rational numbers. This is one that we don't often talk about because we generally skip straight to the real number line. And that's kind of a big idea that I want to talk about. So the rational numbers is the set of all integers when we divide them by other integers. Essentially, this is every single possible fraction that could exist. Right? So take any single integer divided by any other integer, and that's going to be a fraction. This is also countably infinite, which when I first heard kind of blew my mind because I mean it makes sense that the integers are countably infinite with a little creativity, but now we have like almost an infinite number of combinations of the integers divided by the integers. What's the system for lining these up? But I'll show you on the next slide, which is right here. So how is this number system countably infinite? Note that this doesn't include the negative, so you could add a negative sign in front of all of them. But if you line up all of the integers, creating this grid, you can now ensure that you are getting every single possible fraction. You can cross off the non-simplified versions, right? 4/4 is the same as 1/1. So this little diagonal here is all repeated values. But you just skip over those. But now we have that system of counting every single possible fraction that exists, which again means even though there's an infinite number of these, because we can count them, this is a countably infinite set of numbers. So something to note, all of these number systems are nested inside one of another. So the natural numbers rest inside of the integers, and the integers rest inside of the rational number system. So at each of these steps, what we've done is we've taken a number system, we've added something that didn't sort of formally exist previously, and created these slightly larger sets. So before we continue on, we're going to have a quick little note about the Pythagoreans. So the Pythagoreans, obviously, big followers of Pythagoras. Um, like I noted here, I could have done this entire presentation just on this mathematical cult. Uh, these guys were hardcore fans of mathematics, hardcore fans of numbers. They truly believed that you could mathematize everything and make sense of the entire world strictly through numbers. It was the basis of essentially their entire philosophy and their entire religion, right? These were the foundational building blocks by which all of the world made sense. So they essentially were worshiping these numbers. Um, Again, noting that they could theoretically, or thinking they could theoretically describe everything in the universe. Music, we know that music theory is very mathematical. Celestial movements, the stars, that was a huge application of mathematics at the time. They even thought that things like virtue, right, somebody's character, um, in theory, could be represented numerically. So the rational numbers, which we said, Pythagoras is kind of credited with giving, formalizing this number set. These are like an infinitely dense set of numbers. You can get fractions infinitely small, as we'll show on the next page. So to the Pythagoreans, they thought that these are truly the foundational building blocks of the universe. And kind of like how at one point we thought molecules were the smallest thing, and then we realized, oh, you can break those into smaller pieces. Right? But so for the Pythagoreans, the rational numbers was sort of like the end all be all. This is, we've made it. We've found the smallest possible building blocks of the universe. Right? So here's a quick little example showing you how you can get infinitely small. Uh, which again blows my mind that the fractions, the rational numbers, are countably infinite, because even between 0 and 1, there's actually going to be an infinite number of fractions. However, we can count them. There's a countable system by which we can get all of these numbers. Crazy. So how can we show that there's an infinite number of fractions between 0 and 1? Just take half of the distance each time. So in between 0 and 1 is 1/2. In between 1/2 and 0 is 1/4. In between 0 and a fourth is an eighth, then a 16th, 32nd, a 64th, 128th. And you can continue getting smaller and smaller and smaller and smaller and smaller, right? But with our system of counting, we would eventually hit every single one of these fractions. Crazy. Another example, just think about how much space is in between any two fractions as you increase the size of the denominator below. So in between a half and a third, there's 1/6 of a unit. In between a third and a fourth, there's 1/12, and that's getting smaller. By the time you get out to like 100,000 and 100,001, whatever that is, the space between these lines is like 0.000001. Right? You keep going out further and further and further, the space between these numbers is getting smaller and smaller and smaller. You can always get closer to another number. You can get infinitely close to a number. So it made a lot of sense that the Pythagoreans would think that, of course, these are the foundational building blocks of the universe. All numbers, everything can be represented by something inside of this number set. Enter irrational numbers. So you would think that if you add every single fraction onto a number line, eventually you're going to have this nice, smooth, continuous line extending from negative infinity all the way to positive infinity. There is again, I'm not a history person, but when Hippasus, some Pythagorean named Hippasus, he discovered a number that couldn't be represented as a fraction using the unit triangle. There's the rumor that he was thrown out of a boat for blasphemy. Right? This is like going against the church, claiming that there's some new type of number, in the same way that the first negative number probably seemed absolutely wild to people, probably in the same way that um, zero was crazy to people at one time. Uh, I don't know if he was actually put to death. That's kind of a rumor, but it's kind of a fun rumor to that potentially somebody was put to death for discovering a new type of number. In practical applications, most of the time you could find a fraction that's close enough to the square root of 2 in order to find those approximations. So it wasn't necessarily exact, but it was like pretty darn close, and so there wasn't necessarily the question of what this number was. There's a proof of there's a proof that root 2 is irrational. It's at the end of this presentation if you're interested. When If you remember the Pythagorean theorem, a squared plus b squared equals c squared, you'll get that square root of 2. And this square root of 2 is simply a number that can't be represented by some sort of a fraction. We have to introduce a new type of number, which we're calling the irrational numbers. Other familiar types of irrational numbers that exist are pi and e, um, and many other square roots. There's actually an infinite number of these irrational numbers. So what's crazy is that even though the rational numbers are infinitely dense, you can basically get as close to a number as you possibly want using fractions, that somehow there are still holes inside of that number line. And we need to fill in all of those holes with these rational numbers in order to get that nice, smooth, continuous line from negative infinity to infinity. So this is why we pretty much just skip over um, rational numbers in most of our math classes, because we just want to use the nice, smooth, continuous line. And so what we'll do is we'll kind of skip straight to the real numbers. We'll sort of ignore integers, sometimes noting that, yeah, the integers live inside the real number. So if I'm doing some sort of application, I can plug integer values into my function and get out other values. We pretty much never plug in pi to some sort of a function in a real world application. So it makes a lot of sense that we go straight for the real number line, the nice, smooth, continuous function, or a nice smooth continuous line from negative infinity to infinity. But this requires this like crazy step of taking something infinitely dense and then putting an infinite number of teeny tiny holes inside that infinitely dense thing to make it perfectly smooth and continuous. This is also a huge jump because the real numbers is no longer countably infinite. You could count the infinite number of fractions, but now when you have the real numbers, we have a new type of infinity, a not countably infinite type of infinity. So this is now beyond this kind of the scope of my talk, but a quick little bonus note is that there is a further extension of the real number line called the complex numbers. Most of us might be familiar with the term imaginary numbers, which is very unfortunate naming because they exist in the same way that negative numbers exist. They just don't exist in the real number line. It becomes much more complicated to start introducing imaginary numbers. So most of us don't really deal with them in our math classes. Maybe they're alluded to briefly, but for the most part, we stick to real numbers. If you've ever taken the square root of a negative and said it doesn't exist, that's only in the context of the real number line. The square root of a negative number does exist if we expand to the complex numbers. So Girolamo Cardano in the 1500s sort of discovered complex numbers, or at least was the first person to be willing to say, what if we let there be a square root of a negative number? What happens then? Because that seems crazy, right? In the same way that's like, why would we have a negative number? Um, a long, long time ago now, it seems kind of natural to us. Right, so the complex number system is taking the real numbers and then adding on an imaginary number part. So that imaginary number part is simply a square root of some sort of a negative. So in order to represent complex numbers, it requires two dimensions. This is one reason it's incredibly difficult, because if I wanted to graph a complex number to another complex number, this requires four dimensions. And if you aren't familiar, we only live in a three-dimensional world, so it is impossible for me to actually represent this type of a graph other than having a graph of my inputs and a separate graph of my outputs, and somehow trying to, in your brain, plot the two differences between them. All right, so this point right here represents one complex number, A being the real part. So again, the complex number system is an expansion of the real number system. All real numbers are part of the complex numbers. But if we allow taking the square root of a negative, we now have an expanded number system that, again, requires two dimensions. It has two pieces, the real part A and the imaginary part B. Uh, so this is a pretty complex, as I noted, pun intended, topic. So typically we don't see exposure to it, but I believe that in computer applications, it actually comes up quite a bit. If you're trying to create some sort of a system, you can note that if you take I and you square it, you get -1. You get I to the third, you get negative I. Take I to the fourth, you get +1. You multiply I to the fifth, you get I again. So you have this way of sort of cycling through like 90-degree angles on the complex number system, um, 1 being here, I being here, -1 being here, negative I being down here, and you can kind of rotate these things using the complex number system. I'm not going to claim to have ever done any computer engineering. That's kind of the explanation that I've received at some point. Uh, Again, it's really unfortunate that they were named imaginary, because so many students will come to me at some point and be like, yeah, imaginary numbers, it's silly that we have to do these things that are completely made up. But realistically, it's like all numbers are made up. Imaginary numbers are made up in the same way that negative numbers are made up. Yes, it's hard to conceptualize them, but that doesn't mean that they don't exist. Doesn't mean they're not real. So the connection to spirituality. I think I'm going to stop here in the recording and start again another recording, because otherwise these videos are going to be way too long. Thanks for watching. Well, thanks for watching the introduction. Hopefully you will watch more and actually see the connection that I'm hopefully going to be making.